Hello guys, welcome on Tesla Adventures. In this video, today we are going to discuss the motion of a charge in the perpendicular magnetic field. So in this situation you can see that there is a magnetic field which is pointing inside the plane of this screen, and there is a charge Q which is being projected with the velocity v in this direction, positive x-axis, and its mass is m. Now you can see that this charge will experience a magnetic force which could be determined by the Fleming's left hand rule. And if at this position you will open the first two fingers and thumb of your left hand perpendicular to each other, and you will point the second finger in the direction of velocity, and if you will point the first finger in the direction of the magnetic field which is inside this plane, then you will find that your thumb is pointing towards this y-axis. So obviously the force acting on the charge is towards y-axis at this position. Now hence it would rotate slightly, then this force will start to act towards a particular point on the y-axis like that. I'll show you. Like that, and then at this position force would be acting like that, and further on like that, which means that this force is acting towards a particular point which is the center of this circle, and this charge will go on in a circular path. So it is very important that in perpendicular magnetic field, motion of charge, I'll be writing it down. In perpendicular magnetic field, motion of charge is circular, and the plane of this circle is perpendicular to the magnetic field. The plane of this circle is perpendicular to the magnetic field. You can see that this circle in this question is, in this case, is in xy plane, and magnetic field is pointing in the z direction. Okay, so first of all, when a charge is being projected in magnetic field, then it goes in a circular path. Obviously we are talking about perpendicular magnetic field and also the magnetic field which is constant in magnitude. So this charge goes in a circular path, and this circle is in the plane which is perpendicular to the plane of the magnetic field. Now the second important thing is the fact that this is a uniform circular motion. Now uniform circular motion is due to the fact, now you can think that why it is a uniform circular motion, because in each case, in every case, the velocity is perpendicular to the magnetic force. F magnetic is perpendicular to V, which means work done by F magnetic is 0. Okay, so work done by magnetic force is 0, and therefore the kinetic energy of the charge is constant, or we can say that speed of the charge is constant. Okay, so therefore we can say that it is a uniform circular motion. Now the centripetal force role is being played by magnetic force, and magnetic force is QV cross B. You can see that V is always in this plane, xy plane, and B is towards z axis. Therefore V and B are always mutually perpendicular, and obviously force is always perpendicular to V and B. So this is Q into V into B, and this force will be mv square by r. So cancelling V with V, r radius of the path would be mv by qb. This is the radius of the path. Okay, now Now the time period of the motion can be calculated by 2 pi r by v. So t will be equal to 2 pi r is mv by qb divided by v, cancelling v with v. So t will be equal to 2 pi m by qb. So this is the time period. And if we discuss about the frequency, then frequency is 1 upon time period. So it is qb by 2 pi m. And omega, angular frequency, is 2 pi f, obviously. So omega will be equal to qb by m, angular frequency. This is the motion of charge in the perpendicular magnetic field. Now we can say that it is obviously a uniform circular motion, and we have already discussed the power delivered by the magnetic force. F magnetic is always 0, therefore the kinetic energy will remain constant. And it is very important to note that each time this particle will complete the circle, it will again come to the initial point, moving in the initial direction again. Okay, so this is a very important concept. Now we can also check that we can also find out the instantaneous coordinates of this charge, and let us draw the diagram. So let us see. First of all, let us draw the diagram that one second. This is the situation. This is the magnetic field, and let us draw the circle also. This is the circle. Now let us find out the instantaneous coordinates of the particle as a function of time, and also the instantaneous velocity. We know that initially at t is equal to 0, particle started from origin, or we can say that the starting point is assumed as origin, and at this time the particle has a coordinates of x comma y. If this angle is theta, then obviously theta will be equal to omega t. Omega we have already calculated, and v will be the velocity of the particle, like that, in the tangential direction. And x coordinate, this is the radius. Now radius of the particle will be mv by qb, and the x coordinate of the particle will be equal to r sine theta, and y coordinate of the particle will be equal to this one. So this would be r minus r cos theta. So the position vector of the particle will be equal to x I cap and y j cap. So x is r sine theta is omega t I cap, plus y is r into 1 minus cos omega t j cap. This is r vector. And if we wish to find out the velocity vector, then we can again use another diagram. Let us draw quickly. Now at this position, theta angle, velocity is like that. This is v, and this angle is theta, and this angle is theta. Okay, so the velocity of the particle, speed is constant, we have already discussed, and speed v, velocity v would be v cos theta I cap plus v sin theta j cap. Now theta is equal to omega t, so this is v cos omega t I cap plus v sin omega t j cap. So if you will substitute the value of time, you would be getting the value of v. So this was the motion of this charge in the perpendicular magnetic field. So let us summarize quickly that when a charge is being projected in the perpendicular magnetic field, then its motion is a uniform circular motion. The plane of that circle is in the perpendicular direction to the magnetic field. The work done by magnetic force is always zero. The power delivered by the magnetic force is always zero. The kinetic energy of the particle remains constant throughout the motion. The magnetic force plays the role of necessary centripetal force which is required to take this particle in circle. And the time period is independent of the velocity of projection, which means that if the same charge is projected in the same field with different velocities, then the time period will still remain same, but radius depends on velocity, so radius would change. Frequency again is independent of velocity, and these are the coordinates of the particle. You can substitute t is equal to 0. So if t is equal to 0, then x coordinate is 0, and t is equal to 0, then y is also 0. So particle is at this position. And you can also find out the instantaneous velocity of the particle. Now let us take two concept illustration problems to solidify our depth of understanding this concept. So in this first problem, you can see that there is a limited magnetic field which is extending from origin to this point d comma 0, and we have projected a charge q with velocity v and mass m along the positive x-axis from origin, and we have to find out the deviation produced in the path of the charge and the time for which this charge remained in the magnetic field. Okay, so first of all, we have to in these kind of questions, the first most thing which you have to do is to find out the center of the circle. So let us draw the path. Let us see that the force would be, you can apply the Fleming's left hand rule, and you can see that this force would be acting in the upward direction initially, and therefore it would start to bend like that, and at this position it would go it would go in a straight line, because we are assuming that it escaped from the magnetic field. So we know a concept of circular motion, that if we draw two normals to the velocity, then these two normals intersect at the center. So this is the center of the circle, and this would be the radius r. And if this angle is theta, then this would also be theta. So deviation angle is theta. Now in the first case, you can see, let us use the first case, that d is equal to mv by 2qb. So d is equal to r by 2, where r is the radius, which we know that it would be mv by qb. So d is r by 2. So you can see that this is r sin theta, and r sin theta is equal to d. So sin theta is equal to d by r, and d is r by 2, so d by r is half, so theta is 30 degree. So this particle would be deviated by 30 degree, and the time for which it remained in magnetic field can be calculated by theta by omega. We know that t is equal to omega t, theta is equal to omega t. So t is equal to theta by omega, and theta is pi by 6, and omega is we have already calculated the omega. Omega is qb by m. So this is qb by m. So time for which it remained in magnetic field is pi m by 6 qb. Okay, now speed would be same. Now in the second part, if d is equal to qb, so if d is equal to qb, then this particle will move like that. It would come, if this is radius r, this is obviously r, so if this is r, then it would complete the circle and it would go like that. So obviously in this case the deviation theta would be equal to 180 degree and not 90. Okay, because it has been deviated by 180 degree like that. And the time for which it remained in magnetic field is obviously pi by omega. So it is pi by qb by m, and obviously this is the half time period of the total time period. Now if this d is equal to 2 mv by qb, which means that d is equal to 2r, then also the path of the charge would be like that, which means that there would be sufficient distance like that. There would be sufficient distance r and r for this particle to turn back, and therefore theta again in this case would be pi. So the radius, in fact the time for which it remained in magnetic field will be same, pi m by qb. Okay, so this was the first concept illustration problem. Now in this second problem you can see that there is a charged particle, positively charged particle q, which is projected in this magnetic field which is pointing inside the plane of the screen with velocity v at an angle theta at point A. We have to find out the distance of point B from which this charge will emerge out of the magnetic field, and also we have to find out the time for which it remained in magnetic field. So first of all, if you can apply the Fleming's left hand rule, then you would see that force would be like that and its motion would be circular. So this would be the circle. Let us draw the circle. This particle would go like that. Obviously it would not move in a circle outside the field, but inside the field it would move in a circle. So if we join these two normals, then this would be the center, and you can see that this angle C, this angle is 90 minus theta, this is theta, so this is also theta and this is also theta. Okay, so in this case B point is this, and obviously it would emerge out at the same angle theta. So this is radius, and you can see that this distance is 2r sine theta. You can see that this is r, so this is r sine theta, so this is 2r sine theta. Theta is given to us, so we can say that AB distance is 2r sine theta, and r is mv by qb, so it is 2 mv by qb into sine theta. This is the distance, and now the time for which it remained in magnetic field is obviously t is equal to theta by omega. Now this theta is the angle made by the particle at the center, and this is 2 theta in this case, so this is 2 theta by omega. Omega is qb by m. But in the second part of this problem, you can see that this charge is negative charge and it enters the field from this point, and you can see that the force, if you will apply the Fleming's left hand rule, then you will observe that force would be like that. So the circular trajectory of this particle would be like that. I'll draw. This particle will go like that. Obviously again it would be moving in circle only in magnetic field, but circle center would be lying inside the magnetic field, and if we find out the center, then here would be the center, this would be the center, and again this angle would be 90 minus theta, and this would be theta, and this would be theta, and this is B. So again the distance AB, this is R, so again AB will be 2R sine theta. Sine theta is given to us, and this is 2 into R is mV by QB sine theta. And the time for which it remained in magnetic field is quite interesting. You can see that the angle made by the particle on the center of the circle is 2 pi minus 2 theta. So the time will be equal to 2 pi minus theta upon omega. So time will be equal to 2 pi minus theta upon omega is QB by M. Because obviously the particle rotated from this point to this point, so angle made at the center would be 2 pi minus 2 theta. So these were two basic concept illustration problems, and just after this video I would be making video on helical path, and then I would be making 2 videos of level 1 and level 2 problems based on the motion of charge in magnetic field. Guys, I wanted to say a very important thing to you all, that for cracking the Olympiads and the JEE Advanced and the international exams which are based on physics, it is very important that you go through the numericals quite deeply. So I've seen in the recent times that most of the videos which have the concept theories were having more views as compared to the videos having the conceptual questions of level 1, level 2. I think this should be reversed, and I think that the more views should be on the numerical videos, and hence it is due to the fact that the numerical videos are very important for deep understanding of the concepts and the applications of the concept in tough situations. So I would recommend you to please go through those videos also, and I would be uploading those videos soon. Thank you.